Now I will tell you why this basis is terrible and this basis is great. And I could have explained it before, and I think I did on an intuitive level, but this will show you that orthogonality is actually the key. Okay, why is this bad and this is good? We'll go back to the geometric analogy. And you should agree with me that this basis is bad. And this basis is good. And you can say that this basis is bad because it's not orthogonal, and this basis is good because it is orthogonal. So that doesn't really convince me, because from a certain point of view, they're equally good. I need something else that will tell me what makes that one bad, and I'll tell you what it is. But what's good about, equally good about both of them is that they span the whole plane, they're linearly independent, any decomposition with respect to either one of these will be unique. It can be done. Yes, this is easier to do by eyeballing, but we know that's not a fair argument for calling something better than other things. Better than something else because we're no longer in the habit of eyeballing things. We use computers and so on. So what makes this better for an engineer? Makes this better than this? Well, here's what it is. In engineering, in physics, in practice, let's just make the blanket statement that everything's a little bit approximate. So when I go to decompose something, the model for that being approximate is that I might have a vector like this that I need to decompose. But being a natural scientist, I'm not quite sure whether it's right here or maybe right here or maybe right here. I might make a small error in my measurement. Computers make small errors because they round things off. Small error is a fact of life. The question is, how do you deal with it? And this basis will deal with it very badly. Because if I make a small error and instead of this one, I consider this one, then my coefficients will be 2 and 0. Am I right? But if I make the error the other way and I consider this one, now my coefficients are 0 and 2.5. Do you see how a small error made my coefficients go from 2 and 0 to 0 and 2.5? The coefficient changed completely. So a small error in the initial data, in the input data, caused huge errors, ultimate errors, in our analysis. That makes the whole analysis unstable. Whereas if you do it with respect to this basis, being orthogonal, a small error like that would result in a small error in the corresponding coefficients. You can see that, right? You will go from being 3 and 3 for this one to being 3.1 and 2.1 on this one. Small error in the input, small error in the output. Stable. Better from that point of view. But notice that in order to argue that this is better, I refer to lengths because I refer to errors. Right? So once there is a length, once I'm referring to a length, it means I can't escape orthogonality in the inner product. And so, in that sense, being orthogonal is better than having a very, very small angle. Now, how does this carry over here? Again, it's orthogonality. If I were to start plotting these, because on a test, on all the quizzes, you were working with symbolic formulas. So you were focused on the coefficients, and that makes this very easy. But that's not what happens in real life. In real life, you have some data. You have some path. Even if it's what's called pure science, physics. You have the trajectory of a planet. There is just, I don't know whether it's uncertainty, but I want my calculation to be stable. Whether it's for a path of a comet or nearby path of a comet, because the gravitational field of a planet pulled it a little bit. Let's see what this basis looks like. And you'll see that it's analogous to this. Here's x equals 1. Here is 1. Sorry. Here is p equals 1. Here's p equals x. I'm rushing because I know you guys are rushing, so I won't rush because this is important. Here's x squared. Pretty good, right? Now you'll see that with x cubed is where the problem really starts. Here's x cubed. Here's x to the 4th. Here's x to the 5th. Here's x to the 6th. And so forth. They all begin to look exactly the same. And if you have some data, you will never be able to tell, do I have a little bit of x to the 7th in it or a little bit of x to the 8th? That's just an idiotic question. Because x to the 7th and x to the 8th look like these two vectors. If you started plotting Legendre polynomials, in the video I will probably put a picture overlay over it. Here's what you would get. Here is x, no zeros. And we're going from -1 to 1. So here the picture would be different. Similar, slightly different, but similar. So here is 1. Here is x as a single root. Here is x squared minus 3rd. Look at that, it has 2 roots. Then by the time you plot x cubed, it goes through here, right? Cube, yeah, it'll be something like, I hesitate, something like this, right? 3 roots. Do you see how now x cubed looks totally different from x squared? They looked almost the same here, but that little shift, these little subtle shifts, result in a totally different function. Then will come x to the 4th. It won't be x to the 4th, it'll be x to the 4th with x squared mixed in and 1 mixed in. And you'll end up with, I don't know whether it'll top out here, but it'll just have an extra loop. And then x to the 5th one, the 5th order one, I shouldn't say x to the 4th, x to the 5th. The 5th order one will have 5 loops. And the 6th order one will have 6 loops. And they're all completely different. Right? And there's no question whether your data has a little bit of x to the a little bit of the 5th order term or a little bit of the 6th order term. No question, because they're so different. They're as different as these guys. And on an intuitive level, these correspond to the pitches of notes that you hear. You can say that this note on the guitar looks like this, and the next note on the guitar looks like this. A little bit more frequent. Do you see that? And you might look and say, well, they're kind of similar. They're kind of like this. No, they're not. In fact, they're in some sense orthogonal. Your ear can really tell them apart, right? If I could sing, I'd sing you 2 nearby notes, and they sound very different. So don't get fooled by this, by saying, hey, one has wiggles and another one has wiggles too. If they have different number of wiggles, they're very, very different functions. They're orthogonal. That's what makes them different. Orthogonal means different. Sorry, see you next time.